Okay, good morning. Ready for another day? So I like this one, the old system, earth, fire, water, and air. Okay. And you got the mixtures too, right? Like the compounds would be like earth and water would be mud, right? Earth and air, what would that be? Dust, right? And then you got I don't know what fire and air is. Fire and air, that's August in Texas. Okay. Right. And then fire and water, tequila. Right. So, I don't know. So today's agenda, let's go through the ALEKS reports real quick. Really pleased with the progress. This was as of last night. Yeah. And people are rocking along. Got a folks, that are about 8 or 9 that are struggling with this one. So hopefully I'll be able to help you out today. Let's look at the topics that are due. Oh, one other thing too. So I don't know if you guys can see, those of you that have used ALEKS and are like really comfortable with it, can you see on your end the topics learned per hour? This little ray?
I don't know.
You know what I'm saying?
I'm
Like,
trying to get that far.
yeah, so this what I'm seeing on one side, and like the top person in the class is like killing it because they probably had chemistry before, right? They're doing 11 topics per hour because it's review for them, right? That's pretty fast, okay? But some folks are having a real tough time. So again, I'm beating the drum for tutoring. If you're having a real tough time and spending 16, 17, 18 hours, I mean, you're learning some chemistry, but you could probably get some help to there's got to be some core concepts that are slowing you down that you're missing. So I would say get with a tutor and try to move that higher a little bit so that you're more productive in your time in studying ALEKS. There's no stigma to tutoring, believe me. I had to get tutoring in calculus too, you know, and I'm salutatorian in my class. So I walked into college thinking, man, I know it, right? And I get in there to Cal 2 and I was like, dang, what is this? Yeah. So there's no shame in that. Okay. High school tutoring, you know, everybody's like, oh, duh, but not in college. College tutoring is great. Okay, here's some difficulties that I've seen in this one where people have mastered 1% or 0% of this topic. And so I've doubled up on these in today's lecture to kind of give a couple of examples so that you can be strengthened. I'm really happy with the one, understanding periods and groups in the periodic table, 81% mastered as of like 2 days ago, so that's fantastic. So let's go through this. So the periods are the rows in the periodic table, and you can see them over here, and they will be important to us later on in the course. Because when we're starting to put electrons into atoms to build up the electron cloud and figure out what orbitals they go into, like the 1s, 2s, 3s orbitals, and so on, this number is really handy. Because if I'm working with rubidium, I know that first electron on rubidium is going to be a 5s electron. So that's way in the future, but the periods really become important for us to keep track of the shells, the electron shells that we're starting. Okay, and then the groups, those are really important for the valence electrons, knowing how many valence electrons we have, in particular the main group elements. So these all have one valence electron because they're in group 1A. These have two valence electrons because they're in group 2A. The transition metals are a mess, that's why they call them B. Okay, but then we get back to the other main group elements, and then it's 3A, 4A, 5A, and those are the valence electrons. So the main group elements are very easy to know. And you can see that here, the periods and groups in the periodic table. Okay, they have special names. So you've probably heard of the noble gases. It's BLE, okay? It's not Nobel like the Nobel Prize. Okay, then we have the halogens, the green ones here. And then we have the chalcogens. Kind of a weird word. It starts with a CH, but it's pronounced chalcogen. And then this one is crazy. I never learned this one. That's one of those silent P words. So it's a pnictogen. Okay, but it's got a P in the front just to mess with you. Okay. And then over here we have the alkali metals and the alkaline earth metals. So that's what they are, okay? Now, hydrogen's a unique one. It's not a metal, even though it's lined up over there. The reason it's in the group 1 is because it has 1 valence electron. So that's superseded where it puts in the periodic table. Some people will put it over here because it's 1 away from the noble gases, but most of the time you see it over here. But that is kind of confusing because those are the alkali metals and hydrogen's on top, but it's not a metal. And then these in the middle are called transition metals.
The group number corresponds to the valence number of valence electrons.
Yes, for the A's.
For the A's, okay.
Yeah, for the transition metals, they're kind of all over the place.
Okay.
Yeah, so they have their own course, the advanced inorganic chemistry, where you get into the behavior of all the transition metals. We pretty much have to just memorize the cations that these guys form. Now let's use the periodic table. So 14% have mastered this topic. So the question is, which element probably has a melting point most similar and least similar? We have two options, most similar and least similar to 10. So we need to find 10 on the periodic table. Well, that's another one of those that doesn't have the symbol that has a, like, Ti is not 10. Ti is titanium. So we have to know what 10 is. It's Sn. So it's metal 50. So we find cesium here. This column is cesium. It's element 55. Potassium is a K because the Latin name is calcium. Neon is Ne, it's element 10, and lead is Pb for plumbium. Okay. It's 82. So I don't know. I mean, just looking at this page, I wouldn't know. Okay. We need to use the periodic table. So which of these is closest to 10 in terms of the periodic table? Well, right here, 82, lead is right below 10, which is 50. So they're in the same group. So because they're in the same group, they would have similar properties. So that's all that this problem is trying to teach you. They're in the same group, they have similar properties. So the melting point for lead would be most similar to 10. And then these are at least metals. So the metals are more similar than the non-metals. And since neon is over here as a gas, yeah, it's least similar. So neon would be the least similar melting point to 10. And so the main point is, like, let's see which elements are in the same groups. Okay. So if we were asking the same question about potassium versus cesium, they would be more similar to each other than potassium would be to tin or lead or neon. So if they're in the same group, they have similar properties, is the take-home lesson. Okay, metal versus non-metal properties. So this is I had fun making this slide because it's like, how do we observe things? Well, we can look at it, right? When we look at the object, it might be shiny, which is some metallic type property. This is you and your everyday experience, you know, aluminum foil and things like that. Now, sometimes it's a shiny liquid, mercury, so that's a metallic liquid. That's the only example of that, unless you've melted the metal. But at room temperature, 1 atmosphere, mercury is a liquid. So if you look at it, you can tell somewhat the difference between nonmetals and metals. So nonmetals are dull solids, and they might be gases. In your notes, I did a copy-paste error. So I say a brown gas like bromium, but it should be liquid. So scratch out that word gas and put liquid in your notes. I caught that this morning when I was reviewing my notes. So bromine happens to be at 1 atmosphere room temperature, happens to be a liquid instead of a gas. It's over there by chlorine and fluorine, which are gases at room temperature in 1 atmosphere. But very different than metals. Okay, what else can you do to an object to learn what it's like? Hit it with something. Hit it with a hammer, okay? If it dents, that's very similar to what a metal would do. Now, it might have an oxide layer, like a rusty piece of metal. That rust bounces off, but the metal bends and dents. So that would be malleable and can be flattened into sheets or drawn into wires. That would be ductile. So those are properties of metal. If you hit a non-metal, it breaks. Or I don't know how you're going to hit a gas or liquid, but we're talking about the solids at least, like sulfur. Bang on it, it busts. Like a ceramic, you hit on it and it breaks. Of course, it's not an element. You can heat it. So put a torch on it. Okay, what has happened? Does the whole object heat up together, or does one part of it heat up and the other part not? So that's one of the experiments that you could do. Or you could shock it. You could put a battery on it or something like that and see if it conducts electricity. So does it conduct electricity? That's a property of metals. If it's insulating, electrically insulating, then it's a property of nonmetals. It can be thermally insulating or electrically insulating. Those are two different things. Now, graphite is a common exception to that. Graphite, because of the way that molecule is made, it does conduct electricity. But that's an exception. It's a strange non-metal that conducts electricity. So now let's look at the ALEKS type problems. So here we have element 1, and this is 1% mastered. So this is something that most of you struggled with if you've attempted it thus far. So you got to read the experiment and try to figure out how it applies to these properties. So this is what you need to know. Then you got to look at the experiment and make your conclusions. So element 1 is a hard silvery gray solid. It says wires were hooked up to each side and a 9-volt battery is hooked up to an LED, and the LED glows. So it's conducting electricity. Sounds like a metal. Okay, so you would click that. Then element 2, shiny, silvery gray. It says a 5 by 5 centimeter square, only 1 millimeter thick. So what does that tell you? It's thin. Okay, it's pressed into a disc-shaped mold under high pressure. When the sample is removed, it's become lighter in color and now has the shape of the mold. So it didn't break, is the point. It was put under pressure, it's kind of like hitting it, and it bent, it dented it. It went into shape and it held its shape, it didn't crumble. If you do that with ceramic, it's going to shatter and turn into powder. If you do that with charcoal, it's going to turn into powder. Okay, so that's going to be a metal. Any questions on those two? But do you see how we're trying to take our knowledge and apply it to an experiment? The third one is a moderately soft, silvery gray solid, a 5 by 5 square, only 1 millimeter thick, is heated with a flame at one end. Where the flame touches the square, it rapidly turns red and starts to melt, but the rest of the square remains cool to the touch. You see that last phrase? That's telling you what?
It's not conducting
Heat. Yeah, it's thermally insulating. It's not conducting heat, so that's a nonmetal. So I've already hit the button, so you see that it's a nonmetal. The color, though, silvery gray, there are some nonmetals that look silvery gray, and there are some metals that have an oxide coating like rusty iron. Iron's definitely a metal, but if it's got rust on the outside, it's a dull red color. So that may just be the surface. So you can't always go by the color. Scratch it and see if it's shiny underneath, and then that would tell you if it's a metal. Let's do another one. Since only 1% mastered this, let's do another one. So you can hit try another and get a whole new set. Element 1 is a hard silvery gray solid. A 10-gram cube of it is tapped lightly with a small hammer. Just hit it. Okay. One corner of the cube breaks off into 3 or 4 pieces in a collection of small bits. It didn't dent. It broke. Okay, that means it's brittle. So that's a nonmetal. Okay. Does everybody agree? Yeah, okay. Element 2 is a shiny silvery gray solid. Wires are fastened to each side of it. A 9-volt battery is hooked up to light up an LED, but the LED stays dark. So we tested its conductivity and nothing happened, so it's a nonmetal. And then element 3 is a moderately soft silver gray solid, 5 by 5 centimeter square, only 1 millimeter thick, so a thin little plate of it is twisted using 2 pairs of pliers. So if this was a 1 millimeter thick piece of glass and you twist it with pliers, it's going to happen. It's going to shatter. Okay, but if it's metal, it bends and stays bent, so it's malleable. Yes.
So is the can't decide option just if you just can't decide? Or
Yeah. So I haven't seen one yet where they've given me one where it's conflicting, right? So yeah, so I don't know. I haven't clicked that to see. Yeah, so that's a great question. I don't know. So this comes out as a metal. Yeah. This is all in PowerPoint, otherwise I would click try again and see what else we get. Okay, now let's look at some of the properties of, yes. Oh, sorry, thank you.
Not a question other than just an explanation. If you do like keep
working on that for a
Mhm.
really long time, it'll give you one where you have to choose campus side. Like that's
Oh,
the
yeah.
answer.
Yeah, okay. What, do you remember some of the properties that were conflicting? Like it would have to be a
Usually,
weird
like,
one,
because
yeah.
It was really confusing.
Yeah, I know. So it would just be one that just didn't fit into either category.
I think
Oh.
it
It was
also
solid
gives
that
you
they could
less.
cut in half, but it was
Yeah.
still, it didn't break or anything, but it could be cut in half. That was a,
Yeah, because you could cut a non-metal and a metal in half, and so
Yeah,
it.
because if you
Yeah,
give you
that
a
was one I
description,
remember.
like if it gives you like a little bit of a description on like, it was if it gave you like you cut it in half, but it didn't tell you anything else about it.
Okay, yeah.
It says element 2 is a grayish white solid with a pitted surface. A small cube of it is cut in half with a knife. That's all it gives you.
That's all you. Yeah. So you just can't decide. It didn't conduct electricity. It didn't. Yeah. So what was the color or luster of it?
It said a grayish white solid.
Yeah. That, and again, that could be a metal or a non-metal. Yeah. A pitted surface. Yeah.
And there is another one. It says a grayish white solid with a pitted surface. A small cube of it is put into a ceramic cubicle and heated strongly. It melts about not too far above room temperature.
Yeah, but that could be. Yeah.
Yeah.
Yeah. Non-metals have melting points too. Yeah.
Yeah, I took a picture of it and I was like, what?
Yeah, that's good. So those are good examples of I just don't know. Yeah. I'm glad they give you that because it's not always clear, right? So okay, this is a really nice periodic table. I grabbed it out of the OpenStax book because it has the names by the squares, and all the other ones that I've seen, like in ALEKS, it doesn't have the names right on the various squares. So this is a good one. It's in your notes, and you can go to OpenStax and find it, and it'll be nice. Okay, so understanding the counts of protons and electrons. Most people got this one, but we'll go through it. If you're looking at this symbol on the left and you see a charge, there's a positive charge, it's a cation. And negative charge, it's an anion. Now, where did those names come from? In electrochemistry, you have two electrodes. One is a cathode, one is an anode. Okay? Cations go towards the cathode. Anions go towards the anode. That's how they got their name. So positive charges go towards the negative electrode, which is the cathode. So they migrate towards the cathode, because that makes them cations. And the anions go to the anode. So that's where you know that where those were. They're not cations and anions. Okay? So since it's a cathode, they're the cations, and the anode, they're the anions. Okay. So MO plus is a cation. Okay? But then we need to know more information to know what its protons are. So we go to the periodic table, and that top number, 42, that's its atomic number. That's the number of protons. So we can write 42 down right away. Now, electrons. It's positively charged. So the electrons and the protons don't balance. So you have to look at that and say, for me to have 42 and the net charge be 1, I've got to have 41 electrons. I've got to cancel only 41 of those positive charges. So it's the difference between the electrons and the protons gives you the charge on the ion. Okay. Anybody need clarification? All right, so then we look at the next one, the fluorine. It's a oh yeah.
I'm sorry, I do have a question. Obviously.
No, it's good. Don't feel bad.
How did you know that the net charge was 1?
And that charge was 1, just the plus.
Oh,
It's just a plus 1. Yeah, so that we know we have one more proton than electron.
If it was 2, it's like it'd be 2 pluses.
Mm-hmm.
Oh.
Mm-hmm.
But if they don't put the 1 up there.
Yeah, and so that's when we're making ions. That's the balance of protons and electrons, even in a molecule. So like if you have a huge molecule and it's just plus 1, then all the protons in the molecule are all the number of positives and all the electrons are the negatives. And most the neutral molecules, they balance out. But if there's an anion or a cation, we've got an imbalance of protons and electrons. Fluorine, we look at that, we say, well, that's a neutral atom. So we can do that. And then we know that whatever the protons for fluorine are, it's the same number of electrons. So we go find fluorine in the periodic table. It's element number 9. You can see it over here too on the wall. Element number 9. And so then we have 9 and 9. So that's straightforward. Got it. Okay. The next one is a little trickier. Okay. We don't know if it's a neutral atom. Well, yeah, we do actually. We have 32 protons and 33 electrons. All right, so that is going to be an anion. So this 32 is a germanium, okay? And we know it's an anion because we have too many electrons. There are more electrons than protons. And so then we write that Ge minus. So we put that negative charge on there to show that we have an imbalance. So now you guys can nail that one. Now this one was 0% mastered. So I put a couple of these in here. Isoprotonic atoms. So these are atoms and cations. This is one in cations that have 13 protons. So if we know it has 13 protons, it can only be aluminum. Look at the periodic table, 13. Element number 13 is aluminum. So anything that has 13 protons has to be aluminum. Now it can be a different charged ion. So we're looking for only cations. So the positive ions of aluminum. And so here's aluminum with 13. So we could just make aluminum plus, aluminum 2 plus, aluminum 3 plus. We have 13 electrons. We can make aluminum 13 plus. Okay, it'd be a little crazy, but yeah, you can do that. You can't go to 14 plus because it's, there's only 13 protons.
So you just do that all the way down.
Yeah, you could just you could do aluminum 5 plus or something like that, yeah. Okay, let's do another one of these. Example 2. So this one has 21 protons, so it can only be scandium, Sc. Here's 21, Sc, scandium. And we want cations, so positive ions. So we go find scandium in the periodic table, 21, and so we're going to have Sc plus, Sc2 plus, Sc3 plus. So those are 3 different cations that have 21 protons. So this one should be pretty easy. That's all you're just saying. If it has a certain number of protons, it has the same elemental symbol because they go together. Okay, this one's a little different. Now we're talking about isoelectronic. Really important concept. So if you're getting kind of sleepy this morning, slap your face. Okay, stretch your arms. Okay, because this one is really important because this tells us how we make anions and cations in the periodic table. Okay. So neutral neon has 10 electrons, and this says we can do an element, like an atom and an ion. So neon is 1. Neon has 10 electrons. And if we make any ions in this problem, they want anions. They want negatively charged ones. Okay? So here's neon, 10 protons, 10 electrons, neutral atom, no problem. Okay? If I have fluorine, and I want it to be isoelectronic with neutral neon, I need 10 electrons. Well, if I put 10 electrons on fluorine, it only has 9 protons, so it'd be a -1. So fluorine -1 is isoelectronic with neon. That's a huge concept. Because neon's a noble gas, and the electron cloud of a noble gas is really stable. So if I put fluorine into water, or maybe even some situations in air, but mostly when you put it in water, it grabs an extra electron so it can look like neon and make a -1 anion. Because the neon noble gas cloud is a very stable electron cloud. So neon would rather be a -1. It'd rather be isoelectronic. I'm sorry, fluorine would rather be isoelectronic with neon because neon is a very stable electron cloud. And then oxygen forms 2 minus anions. If it can get 2 more electrons, then its cloud can be like neon. So isoelectronic is a really important concept. This is how we form our ions. So since oxygen only has 8 protons, it's a -2 because it has 10 electrons and 8 protons. So I've satisfied the problem, right? Chemical symbol for 3 different atoms or atomic anions with 10 electrons. Yes?
Can you explain again why neutral neon is part of that?
Yeah, because it says atoms. Yeah, and that's all. I was looking at that going, oh, I get to choose a neutral. Yeah. Whereas the previous problem was only like cations. Yeah. Whereas this one allows the fact that I could have a neutral. So I went ahead and picked neon as a simple, like, easy answer because it's got 10 electrons and it's neutral. And then I can put in a couple of anions. Then, yes. Yeah, you could probably. I haven't tested ALEKS on that, but you might be able to do like boron. So if we're at boron, how many more electrons do we have? So this would be neutral boron. And so this would be boron -1, because I've added an extra electron. This would be boron -2, -3, -4, -5. So boron -5 anion would be isoelectronic with neon. I've added 5 more electrons to it, so it has the same number as neon. It has 10. But boron only has 5 protons, so it'd be boron -5. Okay. In that case, the minus I'm using it to indicate the charge, not like mathematical minus. Okay. So, and then same thing with carbon. If I did carbon here, carbon minus, carbon 2 minus, 3 minus, 4 minus. So carbon with 4 extra electrons would be isoelectronic with neon.
Or you still work with like lithium.
Yeah, you could. If you had to make anions, you could just pack it with electrons. Yeah, and since ALEKS doesn't restrict that, I guess it would take the answer. I would hope that they would say, what if a student puts in hydrogen with 9 extra electrons? So H9 minus. Yeah, so it'd be crazy, but it would technically satisfy the problem. Okay, let's do one now with 26 electrons, the same kind of problem, example 2. 26 electrons, an atom and 2 cations. So 26 electrons is iron, neutral iron, 26 protons, 26 electrons, and then we can form a couple of cations. So now we're going to remove electrons to get to iron. Okay, so here we have iron. If I take an electron away from cobalt, it has the same number of electrons as iron. If I take 2 electrons away from nickel, it has the same electrons as iron. If I take 4, so 1, 2, 3, 4 away from zinc, then it has the same electrons as iron. So this is so important because that's really how chemistry is done, is with the electron cloud. So we're adding and subtracting electrons, that's chemistry. Okay, so this is a good set of problems. So we could do iron, cobalt plus, nickel 2 plus. Those would satisfy the problem. Okay, isotopes, 24% mastered. I think people are pretty good with this one, but let's just take a moment to solidify this. This is thallium down here between mercury and lead. Probably the most deadly element on the periodic table, just for trivial knowledge. It'll go through your skin and kill you. Okay, so it's pretty bad poison. So here's thallium. It has 81 protons. Find it there, 81 protons. And so how many protons and neutrons? Well, we know, if we find it on the periodic table, it has 81 protons. So that's real easy right away. Boom, 81. Okay. The neutrons, you need to do a little math because it tells us it's thallium 203. 203 is the mass number, not the number of neutrons. So the way I do this is I write it out using the full notation, mass number, atomic number, and then I make a little math problem. I just subtract the protons from the mass number, and I get 122, and that's the number of neutrons. Okay. So the way it's written kind of sets it up for a nice little math problem. I just put a minus there and a line, and I take the difference, and I get the number of neutrons. The only thing that makes me cringe about that is the protons are positive and I've got a minus sign in front of it, and I don't want anybody to think that the protons are negative, so don't do that. Okay, we're just doing a math problem to find the neutrons.
So protons are always going to be what is on the periodic table?
Yes.
And neutrons and electrons, those are the ones that are
Yeah.
changeable.
Yeah, changeable, and we have to figure them out in some way. The electrons we get to by the charge on the atom or ion, and the neutrons, we actually have to know the isotope. So if we don't know the 203, then we just have to assume we have the natural abundance of thallium or chlorine or whatever. So if the neutrons aren't specified, we have a mixture of whatever nature gives us.
This has like nothing to do. Can you go to the last problem?
Mhm. This one?
Yeah.
Okay. Okay, yeah. And if you do ever miss a deal, then just go to the video, yeah, so that we can make it through the material. You done? Okay, good. Okay, now this is, I think, the last topic in today's homework. So we made it. I was worried I wouldn't get to the last topic in today's homework. This is, I don't think it's hard, but it's harder than the others. Okay. 0% master. So that'll tell you something, right? So we have natural and unnatural abundance. And so the periodic table, let's look at chlorine for an example. Notice how all of these masses are pretty close, like 12 for carbon, 14 for nitrogen, 16 for oxygen. You know, they're very close to whole numbers, you know, or integers. But we get to chlorine and we have like 35 and a half. That seems weird because the like carbon 12 is 6 protons and 6 neutrons. So it adds up to 12, very close to 12. Nitrogen 14, you got 7 and 7. Oxygen 16, you got 8 and 8. Neutrons and protons. So how do we get a half like in chlorine? Well, it's because there's 2 isotopes. And so it's the average of the natural abundance of the isotopes of chlorine on Earth. And so this problem is related to that. And what they wanted to do was set up a problem where you weren't going to just be able to look at the periodic table and cheat and type in the answer on the periodic table. So they wanted to come up with a number that was not on the periodic table. So they said we had this asteroid or planetesimal, bigger than an asteroid, smaller than a planet. Okay, and they've given the name with ALEKS in it. And it's located in the outer solar system, and somehow we got a mass spectral analysis on it. Okay, so robot spacecraft went out there, landed on this thing, brought back some dirt off of that thing, and we analyzed it and found this abundance of ruthenium. So our answer is not going to match, you know, this number necessarily. Okay, I think it does, but it doesn't have to. So this is how we set this problem up. We have the answers from the mass spec. So we have the 2 isotopes, and it was 48% of the 102 and 52% of the 100. So we have our 2 isotopes set up like this, and we have our mass in AMU for each of those isotopes times its natural abundance. And the only trick to this problem really is to recognize that we convert the percentages into their decimal equivalents. So the 0.48 and the 0.52. So the other thing is they want to make sure we take into account significant digits. So both of these have 2 significant figures, which is really a shame because we know the masses really well. We should get a better mass spectrometer, to be honest, because that's pretty crummy to only have 2 significant figures. All right, so we do those multiplications. And here's where I'm saying this concept of guard digits, right? We have 2 significant figures, so the bolded value is where we should round, okay? But we're going to keep these extra digits as we do the addition, and then we'll round at the end, okay? So we're going to pay attention that we're confident to the ones place, okay? And so then when we do this addition, we round at the ones place, because that's where our confidence was. This was our last significant digit, was in the ones place, and so we round to the ones place. So the 0.860 at 0.8, it becomes 101 AMU. Okay, and so then it says draw the little, like there's a little box, you type in 44 and ruthenium, and you put in the 101. So that's what we have. It just so happens that it is this 101. It's coincidence. Let's do another one. Since 0% master disk, let's do it again. Different element, different data. This one is using 10. And again, we still have our 2 significant figures. But we set the same problem up. Isotope 124 here, and isotope 118 here. 10 has 50 protons. I wanted to put that in there just because. So we have 123.9 AMU, and its natural abundance on that asteroid or planetesimal, 0.41, and the 0.59 here. Sometimes you only get one of these numbers. Now maybe not in ALEKS, but in life, you get one of those numbers. How would we determine the other one?
Subtracting it from 100.
Yeah, they have to add up to 100%. Exactly. So 1 minus the 0.41 would give us the 0.59. Okay, 2 sig figs, same kind of thing. We keep those guard digits through the end of the problem, but if we round to the ones place after the addition. Notice what I'm saying. We have 2 significant figures here and 2 significant figures here, but we do not round this to 2 significant figures because we're doing addition. When we do addition, we take care of place value. So the place value that is significant is 1s and 10s, okay? But when we add those together, we round to the ones place. And we end up with 120 AMU. And this is what we would enter into ALEKS as the periodic table for that planetesimal. So it's kind of weird. If we were on a different planet, we would have a different periodic table with different natural abundances of those masses. The protons and elements would line up the same, but all these little average masses down at the bottom would be different. And that's how we tell if something's from the moon or from Saturn or from Europa, whatever. And it is different than this. The 10 here on Earth is 118.7, so round up to 119, and this is 120. So lucky for that planetesimal, they got a little bit heavier 10 on average. Okay, that's all of the topics for tonight. What questions do you have that I can clarify? Yes?
Would you add the periodic table with all the conversions you mentioned last week?
Make myself a note. Okay. Oh, and this is a good time to do this. I want you to print legibly your name, like from front row to back. Okay, so just print your name and pass it back so I can learn everybody's name. We kind of established where we like to sit. And, it seems like everybody's here today. This is my attempt to get to know your names. So this first row, the person in the corner, you need to kind of peek around the corner. Tell her to peek around. Perfect. One, everybody look this way. I need to see your faces, even in the back, please. All right, 1, 2, 3. Okay, good. Now rows 3 and 4. Everybody right here. Let's see, 1, 2, 3. Here we go. Gotcha. This is just for my use. I'm not posting these.
For now.
Don't worry about your hair. All right, everyone in the back, y'all look this way. All right, 1. Just wait for him to look up. Okay. Can you see my camera? 1, 2, 3. All right, peek around the corner. 1, 2, 3. Thanks. Man, this is taking too long here.
It's like a motivator for me. My motivator is
Okay, thank you. I've got that. I've got a note for myself to post that now. Okay. So now let's look at the topics. We'll get started on the topics that are due on Monday, where we start to make compounds and learn about molecular formulas, okay? So to do that, we'll start making ions and predicting the ions. Now we did the isoelectronic with, things like that, but now we're going to see what nature likes to do. Scandium likes to make a cation, right? It's got a 3+ here, so we know it's a cation. But after scandium, we don't know what cesium, chlorine, strontium, and sulfur do. So let's look at the main group ions and try to predict what they'll do. So here's the periodic table. Let's ignore the transition metals for now. So if it's those big blocks on either end that we call main group. So the main group elements are the first two columns of metals, and then over here. And then the noble gases are their own thing, okay? So the main group elements are what I've shown here, okay? So the alkali metals and alkaline earth metals like to become isoelectronic with the noble gases by losing electrons. Because if you look at it, they're pretty close to the noble gases. Let's go over here. Look at argon. It's number 18. What is potassium? Number 19. So if it just loses an electron, it has the same electron cloud as argon. So that's why metals like to form cations. All they got to do is lose a couple of electrons, and now they have the stable electron cloud of a noble gas. Okay. So we can look at cesium. It's an alkali metal. Strontium is an alkaline earth, yes. And so those are going to form cations. And then we look over at the metalloids and nonmetals. They're close to the noble gases if they go to the right. And going to the right is adding electrons or becoming negative. Okay, so those form anions. See that? So chlorine over there by argon, if it gets one more electron, it'll be like the same isoelectronic as argon. And if sulfur gets 2 electrons, then it'll be like argon. So we can go over here, we can find cesium. Here's cesium down here, right here. 55 protons. If it loses an electron, it'll have 54. So it'll have the same number of electrons as neutral xenon. So its cloud looks like a xenon electron cloud, but because it has that extra proton, it'll be positively charged. So cesium reacts very easily to get rid of that electron. Another reason that happens is after xenon, that electron cloud is a nice, very stable ball of electrons. Adding an extra electron doesn't change that ball. It just sort of stays outside the cloud and is easy to remove. So these extra electrons that are added are very easy to remove. Then chlorine. Chlorine is right here. 17 electrons. If it gets one more electron, it'll be just like argon. But it still has only 17 protons, so it's going to be -1. Strontium, here at 38. It's got 38 protons and electrons. If it loses 2 electrons, it'll have 36, just like krypton. And it'll be +2+. And then sulfur, right below oxygen. Everything in that chalcogen column forms a 2- ion. So 16, if sulfur adds 2 more, it'll be just like argon. And its electron cloud still only has 16 protons, so it'd be a -2. So the main group ions are easy. The nonmetals add electrons and become negative, and they try to be that noble gas electron cloud. Cations or metals form cations and lose electrons. Now we start changing gears and looking at molecular formulas or chemical formulas. Okay, chemical formula would be a more general category, and then you have under the chemical formula umbrella, you have empirical formulas and molecular formulas. So in this case, a chemical formula for calcium bicarbonate, and it's just asking you, really this problem is trying to teach you what's going on with the parentheses. So you've got the parentheses here in this 2, and it multiplies everything inside the parentheses. So these are 2 bicarbonate ions. That's why we have a 2. And so how many carbon atoms are in each formula unit? There's 2 in each formula unit because of that parenthesis 2. Oxygen atoms, there's 3 inside the parentheses and there's a 2 outside, so it's 6. Right? Everything inside the parentheses is multiplied by 2. The hydrogen, there's 2 of them because there's 1 hydrogen inside the parentheses and you're multiplying by 2. And then the calcium, it's out front, there's just 1 of those. And if you want to add everything up, like the ALEKS problem just asked you the first question, but I went ahead and asked you every possible one that you could ask about this. So add them all up. So what would we do if we had to add them all up? So you have, let's just count everything inside the parentheses first. So right here, we have 5 atoms, right? 3 oxygen, a carbon, and a hydrogen. So there's 5 atoms times 2 gives you 10, and then plus the calcium. So we end up with 11. So that's not bad, right? Molecular formulas, just count the subscripts. That's the number of that type of element. There's quite a few problems in ALEKS that I really like, making you think of molecules in 3D. Okay, so this is a methane molecule. You can see there's a carbon in the middle and 4 hydrogens around it. They're spread out in all 4 directions of a tetrahedron. And it just says, write the chemical formula for this molecule. So we see that there's 1 carbon and there's 4 hydrogens. So CH4, straightforward. Now, I didn't know this, honestly. I learned this from ALEKS this year. I may have been taught it, but I don't remember being taught it. The rules for writing these chemical formulas. I feel like I just learned them by observation. Well, ALEKS has tried to make a list of rules. And so if you hit the explanation on this, you get these rules. Now, I've condensed it to 1 slide, but it goes on for a couple pages about these rules. There's the examples and everything like that. But this is out of the example, the explanation in ALEKS, these rules. So, of course, the very basics, write a chemical symbol for each element, okay? Capitalize only the first letter, just like the periodic table. Like palladium is capital P, little d, or chlorine is capital C, little l. Okay, so it's not. Don't capitalize the L on chlorine. Use a subscript to show the number of atoms of each type. If it's a 1, just omit the number. So we saw that on the previous one. But number 3 was the one I didn't know. Okay, so it says write the symbols in order from left to right. So it says write sulfur before fluorine because it's on the left. So here's sulfur in column 6A and fluorine's in 7A. So you would write sulfur before fluorine. So if you have a compound that has sulfur and it has fluorine in it, as you're writing out the symbols, put S and then F. Okay? And then also oxygen and sulfur are on the same column. And you would write the lower one first. And so you would write S before O. So that's rule 3. Now hydrogen's an exception to that. There's a couple of exceptions here. And it's saying write hydrogen after all of the elements before group 6 and 7. So like you would say C, let's see, 6 and 7. Like you would have CHOF. Right, so you would write the H's after the C, but before the O and the F. Okay. So here's one that it's got 2 carbons, 6 hydrogens, a sulfur, and an oxygen. So we need to use that rule. So we would write the carbons, and then we write the hydrogens before group 6, which is the sulfur-oxygen group, and then we would write the sulfur before the oxygen. So this is just using those rules so that we come up with the standard chemical formula. And if that confused you, go back to the video because we're running out of time. Okay. And then let's do one more before we go. 2 carbons, 6 hydrogens, and a sulfur. So go into ALEKS. This is all prep for the one that's due on Monday.
So the sulfur doesn't go first, though.
Right.
Lower.
We do left to right. So carbons before sulfur. Yeah. But then we put hydrogen before we get to group 6 and 7. Yeah. So I don't know why I never learned that like as a rule. I just picked up on it, I guess, by seeing formula after formula. But now that we're doing this ALEKS where it's going to check all of those things, we need to have the rules in place. Because I'd hate for you to get the formula right, but it just oxygen before sulfur and get it wrong, you know. Let me have thanks. All right, thank you. Are you looking for? Yeah, you found it. Okay, where's the other forms? You got it. Thanks.
We have topics due tonight, correct?
Yes.
Okay, thank you.
There it is.
Well, it's like something in the air when it starts to rain.
There's a lot. There's a lot.
Three. I'm missing two. Is it back there? Okay. Let's see. Maybe look. Thank you. Thank you. Thanks. Yes.
I've mastered about 2 slices of the pie so far.
Excellent.
Is there an easy way to go back and review those?
When you get to the knowledge check, it'll do a review, and then it will. I know for the knowledge check, that's what the purpose of the knowledge check is. It will go back and hit you with problems from all 4 little modules. Okay? There should be some time. I think it's called open. No, I think open pie time is when you can just work on other slices of the pie. So I think the knowledge check is the only time you get to review. And so that's coming up after chapter 2. So in another week and a half or so, there'll be a knowledge check that opens up as a review for the exam, so that you can go back and review all of those things.
Okay.
Yeah.
Well, I'm assuming it's like very quite similar to the, not like the exam itself, but like this is going to be pretty close to.
Yeah, I'm gonna, and so what I'm gonna do is try to produce